Now let's turn to how to show that two graphs are not isomorphic. By the way, it is not enough to show that their adjacency graphs are not, or adjacency matrices are not equal, because it could be that under a different ordering you do get equality. That would not be convincing to do it that way. A much nicer way to do it is to recognize that if two graphs are isomorphic, they have to preserve certain properties. So for example, if two graphs are isomorphic, they must have the same order. They must have the same number of vertices, because there has to be a one-to-one matching of the vertices. So to show they're not isomorphic, it's enough to show that one of these things that we call an invariant, one of these properties that's preserved under isomorphism, show that an invariant fails. That is, the property holds for one of them, but not the other. So it does vary. It isn't invariant from one to the other in that case, and that would show they're not isomorphic. So here's a list of several things that would be preserved under isomorphism. First of all, the order of the graph, the number of things in the graph. The number of edges in the graph have to be preserved because the adjacency property must hold, so that each edge in the first graph must correspond to an edge in the second graph under that isomorphism. The number of vertices of a given degree would have to correspond as well, and that's a nice property. So if one has a degree 3 vertex, and so must the other because of the adjacency property, and so if one has two of them, the same thing is true of the other in the same way. In fact, the degree sequences have to be the same, and so that's a nice way to do it as well. However, all of those might be the same for both of them, and they're not isomorphism, and so sometimes you have to dig a little deeper and find other things. So one thing is, perhaps in one graph you have a degree 2 vertex adjacent to a degree 3 vertex, but that doesn't happen in the other graph. Then they could not be isomorphic as well. So if you had, as I say, in one of them you have a degree 2 vertex that has a degree 2, and the other one has degree 3 in G1, but not in G2, then that would imply or tell us that they're not isomorphic. So if that happens in one of them but not the other, they're not isomorphic. Also, if one of them has a cycle on n vertices as a subgraph but the other doesn't, so you can look for these cycles in there. And also paths. Remember, a path just being something of that sort right there has a path of length n, and the other one doesn't, then they're not isomorphic. So I'm going to give you a few examples and show you how to then show that the graphs are not isomorphic. So let's take the first one to just be these two graphs here. So this one will have 5 vertices, like so, and that's G1, and then G2 will be the graph that looks like a rectangle and looks like that. Now they both have order 5. They both have 6 edges, so that's not helpful. However, you can see some differences here. G1, for example, has 2 vertices that are of degree 3, where G2 only has 1. Another way to show that they're not the same is to notice this isolated vertex in G2, a degree 1 vertex in G2 that G2 does not have. So just pick one of those to finish your statement. So maybe since G2 has a vertex of degree 1, but G1 does not, G1 is not isomorphic to G2, right? So that'd be a nice way to say it precisely. As a second example, let's take these two graphs here. That one, so that'd be G1 in this case, and let's take as G2 similar sort of graph like so. So again, they have a lot of similar features. They have the same number of vertices, 8, order 8. They have the same number of edges, 10. They have the same degree sequence. So the degree sequence is 3, 3, 3, 3, 2, 2, 2, 2. Guess I got it all. Yeah. Darn. Both of them have that. So is there anything here that one has that the other doesn't have on that list above of 6 different invariants? And I guess the one that sticks out, there's actually a couple of them you could come to, but the one that is easiest to express probably is the fact that here we have a couple of degree 2 vertices that are adjacent, but no pair of degree 2 vertices is adjacent in G1. Okay, there are different things, but let me go ahead and say that one first of all. So since G2 has 2 degree 2 vertices adjacent, but G1 does not, G1 and G2 are not isomorphic. Slash through it to indicate that. Now you might have seen something different, and there's certainly a lot of differences that come up here. So for example, if we look over here, there's a 4 cycle here. There's a lot of 4 cycles around in here. There's a 4 cycle here of degree 3 vertices, and there's no 4 cycle over here of degree 3 vertices. Okay, they do not form a 4 cycle. It's a little hard to just use sizes of cycles, because the sizes of cycles match up pretty well as well. But those two ideas would be, either one would be fine. Just pick one and work on that. Don't do more than that. So maybe I'll do another one here. Let's just see if we can do something like this. What do you think about these two? Do you think they're isomorphic or not? And maybe take a minute to pause it, and after I've drawn them, and make a decision: are G1 here and G2 isomorphic? And if so, what would the isomorphism be? And if not, what's the invariant that fails? So I haven't labeled them, but if you want to put an isomorphism there, you're going to have to label them as well. So there's G2, like so. So maybe pause, think about it, and come back after thinking about it. Maybe label them yourself and see what you'd put down for the isomorphism to see if that would work out. Right. So let me go ahead and conclude it here. The thing that's happening over here is that there's a degree 4 vertex adjacent to 2 degree 2 vertices. Over here, that degree 4 vertex, and there's only one of them, is adjacent to a degree 2, but only one of them, because that's degree 1. So they are not isomorphic, and so I would say it this way: since G2 has a degree 4 vertex adjacent to 2 degree 2 vertices, but G1 does not, G1 is not isomorphic to G2. Right? So there's 3 interesting examples to show you how that works, and your worksheet will have a few of those for you to work on as well.